We're going to begin our study of Chapter 3. In Section 3.1, we're going to be talking about maximum and minimum values. Just to give you an idea of what Chapter 3 is going to be about, a large portion of Chapter 3 is going to be about looking at how the first and second derivative give us information about what the graph of a function looks like and what its behavior is. And then towards the end of the chapter, we're going to use that to look at some applications. But like I said, a large part of the chapter is going to be focused on how the derivatives affect the shape of the curve. So one of the most important aspects of a function is the maximum and minimum values. What we're going to discuss here in this section is how to pick them out from the graph and how to find them without a graph over a closed interval. That's what we're going to be doing in this section. So let's begin with the definition of absolute maximum and absolute minimum. Let f be a function with domain D containing a point x equals c. We say that x equals c is an absolute maximum on D if f of c is bigger than or equal to f of x for all x in D. In other words, if that corresponding y value is bigger than or equal to any other y value that you'd get out of the function over the entire domain. It's an absolute minimum if when you plug that in, the y value you get out is less than or equal to any other y value that you'd get out throughout the entire domain. The extreme value theorem talks about when we can expect to have an absolute maximum or minimum for a function. The conditions that we need to guarantee this is we need a continuous function and we need to be working over a closed interval. So we're looking at a continuous function on a closed interval. If we have those conditions, then we're guaranteed to have an absolute maximum and an absolute minimum. Now, I also want to talk about a local or relative maximum. This book and several other books use the term local or relative kind of interchangeably. So let's start with a function f. Same setup. We have a function f with domain D containing a point x equals c. We'll say that x equals c is a local or relative maximum if the corresponding y value that you get out is bigger than or equal to all of the other y values. However, we're just looking at the y values in some small interval containing x equals c. That's the difference between local and absolute. Local minimum, the same idea. X equals c is going to be a local minimum if the corresponding y value is less than or equal to any other y values if you're just looking at some small interval around x equals c. And there's a theorem that addresses what we can kind of expect here, when we can expect this. So if f has a local maximum or minimum inside of the domain, but not on the edge, and f prime of c exists, then the derivative must be 0 there. Now this is kind of unfortunate because things would be really easy if this is an if-then statement. If it has a local maximum or minimum inside the domain, and as long as the derivative exists, then the derivative must be 0 there. If it were kind of phrased in the reverse way, if the derivative exists and if the derivative is 0, then it's a local maximum or minimum. That's not true, unfortunately. That would be really nice and easy if it were true sort of in the way we would kind of hope, but it's sort of said in kind of the wrong way, if you will. And this is why much of the chapter, I would say up even past the halfway point in the chapter, is devoted to this question. How can we determine whether or not we have local maximum or minimum for a given function? Just because this theorem sort of doesn't sort of answer the question. It sort of partially helps, but doesn't fully answer the question. All right, what we're going to do first is we're going to look at some graphs to see it, just trying to get comfortable with the terminology. Can we get comfortable with the terminology of local and absolute maximums and minimums? Now, we call these things to talk about maximums and minimums. They're also called extrema. Just to make sure that that's clear. Okay, so in example 1, so find the local and absolute extrema for this given function. All right, let's just go through the list. Let's go after the absolute extrema first. Okay, so absolute max. Is there an absolute maximum? Well, it appears that there is right here. There's an absolute maximum right there. This y value is going to be bigger than or equal to any other y value throughout the entire function. The corresponding x value is how we're going to talk about our answer here. So there's an absolute max at x equals, it looks like it's about 1.5, with max value. So the y value there appears to be 4. Okay, so let's do the absolute min. Is there an absolute minimum? Well, if you can see that with these arrows here, that the graph continues to the left indefinitely, and the same thing to the right. So we can't say there is no absolute minimum because it just keeps on going, keeps on going. You can't really say that the absolute minimum value would be minus infinity because our answer is only in terms of real numbers, and plus or minus infinity is not a real number. So we're going to say that there's none because there is no smallest value throughout the entire domain. All right, let's answer the question in terms of local. So local max. Well, in terms of a local maximum, we actually have the same answer. This is also a local maximum because you can find a small interval around x equals 1.5 so that if you're looking at the corresponding y values, this is the largest y value throughout that sort of that restriction. So of these y values, that one in question, the one at 4, is still the largest. So you can still say it's at x equals 1.5 with max value y equals 4. Okay, so that's the difference between absolute maximums and local maximums. Now, what about, is there a local minimum? Well, the answer is still no. There's going to be none. Because it doesn't matter. So for a local minimum, what you would have to do, so say this is the local minimum right here. It's not. But let's say this was a local minimum right here. You would have to be able to find a small interval, an open interval, where these are parentheses, not including the endpoints. You'd have to find a small interval around it for which that is the smallest y value throughout. So of all of these y values in question that we're looking at here, this one would have to be the smallest. The problem is as you go to the right, go to the right, go to the right, you get smaller and smaller and smaller values. But there is no smallest value because this was an open interval, not including the endpoints. And so it doesn't really matter what you pick as your x value. When you try to go through this process, you're not going to be able to find a smallest y value throughout just a small portion of the graph. All right, let's make a slight alteration to our graph. Ask the same question. Find local and absolute extrema. So absolute max. We still have an absolute max at the exact same place, at around x equals 1.5. Okay, and we would say the maximum value, again, would be y equals 4. That's how we talk about things in terms of the language here. But now, since the graph doesn't continue indefinitely to the right and to the left, we actually have an absolute min. we have an absolute min right here. And it appears to be at roughly, what is that? Negative 2.3, we'll call it. This isn't really anything. This isn't going to be a maximum or a minimum value in terms of in an absolute sense. What about local? Local max and local min. Well, let's go back and look at one key aspect, local max and local min, in terms of the definition. Now, it's a local maximum if at that particular x value, the corresponding y value is bigger than or equal to any other y value in some small interval, in some small open interval around x equals c. So here's the important point. We're looking at small open intervals around that particular point. So we're not going to have a local minimum at all because you can't pick an open interval around negative 2.3 because the graph just kind of ends there. There's nothing over here to be able to pick an open interval around there. So we would say none here. Okay, local max. If it's an absolute max, it's going to be a local max as well. So 1.5. And this is not going to be a maximum or a minimum, like I said. All right, this is kind of an interesting example here. Find local and absolute extrema. Absolute max, absolute min, local max, and local min. Okay, let's go through the process looking for these things here. All right, absolute maximum. Well, we would like to say that this is going to be an absolute maximum right here. The problem is that there's no point there. So there's going to be none. There is an absolute minimum right here. This is going to be the smallest y value that you see on the graph right here. So it's occurring at x equals -1. And I'll say with min value y equals, what is that, negative 1.5? Okay, so local max. There's not going to be a local maximum either. We can't choose the endpoints. Endpoints are not going to be local maxes or mins, so we don't need to look there. We would want to be looking here, but we run into the same problem. It doesn't matter if you put an interval, a small interval around x equals 2, and look at the corresponding y values in there, these in particular, there is no smallest value or largest value. Because if you say, well, let me pick this value right here, well, you can pick something ever so slightly to the right because this is an open circle right here. And the same thing down here. And this point right here doesn't help at all. So there's going to be none. None and none. The problem here, so why did we get absolute maxes and mins in the last example but not in example 3? Look at what we had. We had a continuous function on a closed interval. It's on a closed interval because its domain is from -2.3 to 4. This is the domain. This is a closed interval because it includes the endpoints. So it's continuous over a closed interval, which means the extreme value theorem says we're guaranteed an absolute max and min. However, here, we did not have a continuous function. We had a closed interval for its domain, but it wasn't a continuous function. And that's what sort of messed up the fact that we didn't, this is why we didn't have an absolute maximum. All right, let's look at, this is an ever so slight change that we made to this example right here. Let's go through and look at the same questions. Absolute max, absolute min, local max, local min. Alright, so absolute max, there is going to be none. This would be the candidate right here for the absolute maximum, but there's no point there. So there's none. Absolute min. This would be the candidate right here. This would be the smallest y value, but there's a hole there. So we're going to say that there's none. Now you may say, well, why can't I choose this? Because if you go ever so slightly, if you go over to this portion of the graph, there are y values that are smaller than it. But there is no smallest value, because it doesn't matter what you pick. If you pick this one, you can always find something smaller. This one. If you pick this one, you can always find something smaller, and there is no smallest one. Okay, local max. Local maxes and mins, we don't look at the endpoints. So we're going to run into the same problem. We would want to look at what's going on around 2. Oh, excuse me. So we'd want to look at what's going on around 2. Look at the corresponding y values. In terms of a local max, we would look what is the largest y value you have over this restriction. Well, over this restriction, it would be at x equals 2, but there's no point there, so there's none. However, there is a local minimum right here, and this occurs at x equals 2. This is going to be the smallest y value in this small interval that we chose here. So with min value of what? Oh, no, excuse me. No, this is okay. Yeah, with min value of y equals, what is that? -1. There we go. Okay, so we only had one of the 4 in this case. Again, because we had a function that's not continuous, and we did not have a closed interval. So you can have kind of anything happening here. We're going to go ahead and stop here with this video. If you'd like to practice some WebAssign homework problems, I think you can do problem 1, 2, 3, 4, and probably stop there. In the next video, we're going to start looking at functions without the graphs to see if we can answer some of these same questions.